of that package is, I think, about a centimeter per side. It's a very small device at extremely low power. And I believe the drift rate was marketed as 7 degrees per hour. Yeah, and we run longer field experiments where that was the rate, roughly the rate that we experienced over an 8-hour period.
Okay, and so in the tilt compensation, did you write that filter yourself?
The rotations, the transform from an image to the spherical coordinates was directly through the fisheye lens calibration package.
Mm-hmm.
We did re-implement it in Python so we could do it live because it's a MATLAB library. But it turns out not to be really all that complicated. Once you have the calibration terms, it's a fourth order polynomial that models the lens distortion.
Mm-hmm.
And so it's really convenient because it goes automatically into the spherical coordinates from the pixel coordinates of the image.
Okay.
And then allows us to use the roll and pitch from the IMU directly.
Right, so how did you get the roll, does the IMU spit out roll and pitch?
Yeah, well, we fused the gyroscope and the accelerometer data.
Right, so how did you do that fusion?
So that was done with a complementary filter, just a simple.
How does that work?
So it does a weighted combination of the accelerometer and gyroscope values over time. There's a little bit of tuning parameter. I think it was 0.98 or 0.098 was for accelerometer. To give more heavily weight the accelerometer values than to help curtail the drift from the gyroscope measurements.
And is this something you wrote yourself or a piece of code you got somewhere else?
Well, Eugene helped me write that, but yeah, that was all the code for this was written in-house. Used OpenCV for the computer vision algorithms, but it was a novel approach for the detection, using a combination of algorithms.
And can you explain the various frames here? Because I'm not.
Yeah, it's unfortunately the lines drawn on these spheres, the great circles, aren't visible. So this one is shown with the horizon on this sphere level to the ground, and then this one is shown rotated.
Might I suggest blowing up the photo in the slide just temporarily so
Sure.
the rest of us can see it, if that's not too much trouble. Still not good.
I'll get a full image there. You can at least see the coordinate axes. The other lines are a pale blue, so they're really not, the great circles aren't showing up. But this shows a rotation, the Z and or the X and Y axes and how it's displacing the local Z coordinate axis. And so when we have the image, it appears that the sun is in its actual location, even if the rover were tilted. So the way this is shown is a little bit backwards. But at first, when we capture the image, it assumes that that image is correct, and it just detects where the XY coordinates of the sun are within that image, without any correction first, and then it projects it onto an unrotated unit sphere, and then to correct for the rotation of the robot, it will rotate that unit sphere the opposite direction of the roll and pitch that the rover is currently at, so it'll undo the effect of rotation on the sun's position in the sky. And that was tested to get all the negative ones correct on the transforms using the three-axis gyro, or three-axis gimbal that was made out of the rotary table and the hand tilt units from.
So this gives you observed azimuth expressed in the robot frame.
In the, relative to a robot frame that has been corrected for the rotation. So we end up with as if the rover were actually flat, we would get the same result as if the rover were tilted.
So it's a flat means a plane
I mean,
that's tangent to the
flat,
sphere?
yeah, tangent to the sphere of the planetary body. Which is what the ephemeris assumes is.
Okay, so I guess this assumes that the gravity vector is orthogonal to that.
Yes, it does. Yeah, it does assume that it would be.
Does that hold well for most planetary bodies?
There are some gravitational anomalies. I know they're well defined for the moon's surface, so we would be able to have that. I believe you would be able to correct for that, at least for the moon. I know it's well mapped. I don't know offhand if Mars or some of the other bodies are. I think that the error here would be such that it would not affect the bearing. If it did affect the bearing a little bit, it would cause a little drift in the path reconstruction, but since it's an absolute bearing, the error essentially resets every new heading.
So how would you go about evaluating the extent to which the error associated with that assumption affects the end result?
Well, we could simulate that looking at the known gravitational anomaly fields for surfaces, and especially looking at the depending on the resolution of those, the gradients involved, because that would be the real problem. Because it'd be easy to calibrate it when you first start, if you're relative to maybe a lander or something that has more sophisticated positioning capability. So yeah, I would assume you could use that gravitational field information to compensate for the change in the gravity vector.
Okay, I have one more short question before I pass the baton to the next person, and you have 15 words
Okay.
to answer this question. So what do you give me that Lambert didn't give us in 2011?
High rate, or much higher rate absolute bearing using only wheel odometry and replicating their level of error.
Okay, next time it comes around, I'll ask why I care about that.
Okay.
That's all right. For now, I'm going to pass on to
Sure.
the next committee member.
Okay, can you go to slide, 27, please.
Sure.
You added 2 slides, so it's in the.
Oh, sorry.
That's
I
right.
just deleted those slides. Maybe I didn't update the numbers yet. So should it be this one?
No, the one showing total error.
Here?
Yeah.
Okay.
So what does total error mean in this case? Is it
So in this case,
the
it's
error
the-
at the end?
It's
or
the error
max?
all along the path. So this, in terms of the distance traveled, this is showing the error at every time step in the path reconstruction. So the very end here, this value is the error at end of path, the 3%, yes. And that's 3% of the total driven.
Okay, but
So
it
you-
is at the end.
Yeah, that one is at the end. It would be, you could look at it along the whole thing. That might give you a little bit of interesting information.
Yeah, so you can look at where you end up, you can also look at what was the max, because it looks like where you
Right,
end
yeah,
up is
it did
slightly
drop
lower than
earlier, so
the
it's like,
max.
yeah, you're right, I probably should look at the max on there instead of just quoting the very end value. Because, yeah, as you can see in the path reconstruction, it curves back.
Yeah, and-
You know, it curves back and the error reduces, mostly due to luck there at the end.
Yeah.
You know, so instead of 3%, it's probably closer to 5 or, but not substantially greater, maybe 6, if it had continued to drive.
What does substantially mean?
So in this case, I guess I'm comparing to the Lambert data as kind of a yardstick, where they were using the space grade sun sensor and visual odometry. I believe also, I believe they were counting the wheel odometry from the wheels and correcting. This was not actively driven, this was pushed by hand for 10 kilometers across the mountains. But here they list the different distances. They range all the way from about 124 to, I think some of these are in the 600 range. And this column is their percent error at the end using visual odometry, and this one is visual odometry combined with the sun sensor. And so for their 300 meter treks, or the ones in that range, you know, there's this about 6% error, 4, 11, 4.3. So we were really close
that's
to
the visual odometry.
and that's that's the visual odometry.
The sun
Yeah.
sensor.
Yeah.
is-
And so they sometimes it was the same error, and other locations it was drastically reduced using the visual odometry and the sun compass to correct. A lot of it was areas that didn't have a lot of texture, so the visual odometry didn't measure the relative turn very accurately. So they benefited hugely from the solar compass in that respect. It would be interesting to see how much it could help with the driving that we did, because wheel slip and wheel stall was a significant issue, and the source for most of the error in that path reconstruction. If you watch the video, you can actually see a location where the path reconstruction pauses, but the ground truth keeps moving. So right here in the beginning, there we
Yeah.
lose about a meter or two, and so there are a couple areas where that happened that degraded our results a little bit, but it still turned out to be very good results, especially with the complexity of the calculations we had to do to get the results, and the cost of the equipment. It would have been interesting to see how low a grade of IMU we could have used to still get the same results. Because, like I said, since you're not integrating the error that you're getting, it's kind of, the error you're introducing is kept at the uncertainty of the accelerometer that you're using. Instead of, a yaw gyro.
Were all the experiments done with the same IMU?
What's that?
Were all the experiments done with the same IMU? Or I guess
Yeah. This was just one run here. We did another longer one, but there were issues with clouds and ground truth to full inclusion. So that information isn't included here. And I didn't get a chance to put the details of that in the report.
Is there any calibration information?
Yeah, so we don't have the specific values in there, but I could put those in there in the report. And there aren't any long appendixes with the code, but the digital copy might include that, and that has the calibration matrix hard-coded in, along with the constants for counts per revolution of wheels and wheelbase information.
How did you decide how underexposed to go?
That was kind of done experimentally. So looking at the results, and it kind of drew from our experience previously in other field tests with the actual sun. The first longer field test we did, we weren't calculating sun heading live. So in this case, we were able to tune the exposure, the brightness, intensity, and the area size threshold for the light at the beginning of the test before we started recording data, so we were able to do a pre-calibration before the run to make sure that it would, when the artificial sun was occluded, we weren't going to pick up the other lights. So that was the intensity cutoff. But we could still get it when only a part of the light was visible. And sometimes when it only seemed like it was a few pixels that were visible, they had such high intensity that they were still accepted when other noisy spots that were very, very small amounts of pixels. Oh, thank you very much. Because there were other things, like the lights at Lafarge on top of some of the buildings, we were able to get some of them. Well, they've got some of those big industrial lights out there. We were able to get some of them turned off by taping flashlights to their sun sensor, photo sensors, and that worked. But some of the other ones we were inaccessible and did show up from time to time. But this algorithm was able to ignore those even when the sun disappeared. So it wasn't always just finding the brightest spot. It had a little bit more intelligence about how to ignore noisy things like small reflections.
When you showed the heading, you showed the one big error that happened.
So there were two of those
Okay, two.
that were
Yeah.
outlier. There was 2 out of about 8,000 images that were incorrectly measured. And so there was an automatic filter that looked at change in heading from, in a second and would eliminate values that were unrealistic. And
Okay.
in that case, it was like a full 360 the rover would have had to do in 1 second.
Okay,
Which-
so that
So
did
that was
not
safeguarded
affect
against
your
that. Yeah, that didn't
overall
affect- yeah,
results because it
yeah.
was filtered out.
Yeah, it wasn't reflected in the path, that spike in
Okay.
yeah.
And what was the frequency of that you were recording?
It was about 0.9 hertz, because it was 1.2 seconds between images on average for the sun sensor, and that was limited only because we were storing all the images. We could have run it faster and not stored all the images, but we wanted to be able to rerun the data set exactly as we did in the field test. So